So hello and welcome in this natural convection lecture series. So previously I have shown you the order of magnitude analysis for the case of a vertical isothermal flat plate and the natural convection over it. So the plate is having higher temperature than the environment, and I have told you that there can be two regimes, Prandtl number less than 1 and Prandtl number greater than 1, based on which we can compare that whether the inertia force will be important or the viscous force will be important, and obviously by the common sense, because we are studying natural convection, the buoyancy force has to be important, right? So now we will look at the exact solution, right? So first of all, I have already mentioned in the last lecture that here we will not assume something like this or something like this, okay? So in other words, we will not assume any kind of competition between inertia force and the viscous force, right? So here we will consider that our inertia force, viscous force and buoyancy force all are there in the game, okay? So with that thing in mind, let us proceed with the governing equation, okay? So I will write the governing equation again. First of all, continuity, right? So continuity, the continuity reads del u del x plus del v del y, that is equal to 0, because the flow is 2D, we have considered it as 2D. Now the x momentum, okay. Another assumption that will still be valid here, that is the boundary layer approximation, that is the boundary layer assumptions, we will consider that these are valid here, okay. So now according to that, if the flow is steady, then the equations will be this, right? So okay, rho into this equal to, now del p del x, and I have already shown you that this we can write as the viscous term and g beta infinity, right, t minus t infinity, right, into rho infinity, if I am not wrong. So actually I have tried a lot to uh, remember all these things, but every time I fail. Okay, so now this time I am right. Okay, so t minus t infinity and rho infinity, clear? Okay, the y momentum equation will not be important here because it is just the del p del y is equal to 0. And now the energy equation. So the energy equation reads that your u del t del x plus v del t del y is equal to alpha del 2t del what, del y2, clear? Any other term? I think no, there should not be any other term. Still we will see that what was the exact equation to be in the safe side, okay. So energy equation, where was the energy equation? Yes, this is the energy equation and we are right, okay, clear. So first of all, because we have considered the boundary layer theory to be valid, then something we already know from our boundary layer analysis. And what do we know? So if I have to, okay, first of all, what do we know from the boundary layer analysis? That is the u by v, okay, or in other words, from the continuity equation directly, U by L is of the order of V by delta, okay, and V is of the order of U into delta by L, and this delta by L will be much lesser than 1. That is why this V will be much lesser than U. Clear? So this delta here is the thickness of heated layer, okay, thickness of heated layer. Because neither we are considering that our Prandtl number is much greater than 1 or much less than 1. So we will concentrate in the region of the heated layer, okay. So this we know, and what else do we know? So right now actually we don't know this delta by L, but here we will use the order of magnitude analysis to find the order of this delta by L. So why should we do that? Because I have already told you that we are doing the exact solution. So why do I need to find the order of magnitude of this delta by L? The answer is because we need to write now the non-dimensionalized equation, okay. Non-dimensionalized equation, okay. So if I need to find the non-dimensionalized equation, I need to know that with which I will non-dimensionalize the terms. So U is equal to U by UC. So what will be this UC that I don't know? How can I know that, right? Let us talk about it later. V bar is equal to some V by Vc. Again, what else do we have? T. Now T, so whenever you are non-dimensionalizing, there should be two objectives, okay. First of all, the most primarily, the primary objective should be, if you have already done my lecture of the convection or the advanced conduction series, then I have explained ample amount of times that the primary objective is to make the mathematical description simpler, to make the mathematical description simpler. For example, that if you have a boundary condition, that is x, or okay, at x equal to 0, your t has some value, your t has some ti. So if you can non-dimensionalize this temperature in such a way that you are saying that at x bar equal to 0, my t is equal to 1. So now, sorry, my t bar is equal to 1. See, for this kind of non-dimensionalization, whatever your ti may be, your t bar would, no matter whatever this value of ti be, your t bar will always be 1, okay. That means your boundary condition becomes, what should I say, becomes independent of your actual boundary condition, okay, and it is represented by some simple numbers like 0 or 1. So this thing has, immense significance in terms of mathematical solving, okay. So this should be your primary objective. Now here we will not forget that objective, but along with that, our second objective is to make all the terms comparable to each other, to make all the terms in the equations comparable to each other. What do I mean by that? So this is the I or inertia term, this is the viscous term, and this is the buoyancy term, right? So you will see that all these terms are in the same order of magnitude if my Prandtl number is of the order of 1. Okay, if my Prandtl number, I am not considering any kind of limit, that is, it is much lesser than or greater than 1. Now, if you consider the actual Navier-Stokes equation, the full x momentum equation, okay, that is, it will again have the term like mu into del u del x square, okay, and in the energy equation also it will have alpha into this plus delta t this, okay, plus all other terms plus the viscous dissipation term. Now here we are considering that the flow is a very low Mach number flow, that is why we can say that the viscous dissipation is not important. Now whenever you will have other terms, okay, you will see by the order of magnitude analysis that that not all the terms are of the same order of magnitude, okay. But now you have to non-dimensionalize the terms in such a manner that all the non-dimensional terms should be of the same order, or if they are important they should be of the order of 1, okay, or of the same order. They actually can be order of 100, order of 200, but they should be of the same order. By this thing, what will happen when we will be non-dimensionalizing the equation, there will not be any kind of spurious surge of terms when we will be solving the non-dimensionalized equation, because all the terms are of the same order of magnitude, okay. So if you are not understanding this, just wait and watch the video. I think that you will understand. So what I am trying to say is this u bar should be of order of 1 and this v bar should also be of the order of 1. So first of all, we know for sure that this UC and VC are not all the same order because of this thing. UC is much greater than the VC. So how can I mean if I choose my UC and VC from here, okay. So how can I choose my VC and UC? So I should have been said that my U and V are not of the same order. So how should I choose my UC and VC so that this U by UC and this V by VC becomes of the same order? That is my challenge. Have you understood? So if you haven't understood the significance of doing this, just wait and watch. But my objective is that I have to choose judiciously this UC and VC so that this U bar and V bar, which is the combination of UC and VVC, they should be of the same order, okay. So let us see that how we can do that. Clear? Okay. So first of all, let me define what we already have. So how can I define this T? So now during defining T is always be, T has to be of the order of 1. So for that, what can I do? And another thing is I should have defined this T in such a way that the boundary conditions should be very much easy, okay, very much simpler. So at y equal to 0, my T is equal to T surface. So if I do this like this, that if I do this by Tc, so that means if I use this formulation of T, it will make that at y bar equal to 0, my T bar will be 0, or I should denote it by theta, okay. So now what should be this Tc? Let us look at another boundary condition. At y bar tends to infinity, I will not say that y bar tends to delta, okay, and okay, that is clear. So now at y tends to infinity, okay, y tends to infinity means it is much greater than the boundary layer, okay. And if I say that my y bar by my y by yc, this is tending to infinity, that means my y is much greater than yc, and this yc we know is delta. So these are very subtle concept, that is the actual boundary condition should be this, my y by delta is tending to infinity, okay, because this is something that is of the order of 1. This is something that is of the order of 1 and this is not of the order of 1, okay. This y is actually of the order of delta, okay. So if I tell that my y is tending to infinity, then I am going beyond the boundary layer, then I am going much beyond the heated layer. But if I am saying that my y by delta is tending to tending to infinity, then I am inside my boundary layer, but still it is saying that I am at this kind of region. Okay, that is inside my boundary layer, but still much away than the wall. Okay, so these things are very subtle. Okay, so at y by delta tends to infinity, I will have my t is equal to t infinity, right? So now let us see that if I choose my Tc as T infinity minus Ts, T infinity minus Ts, then I mean what can I have? So then my theta is equal to T minus Ts by T infinity minus Ts. That means at y bar tends to infinity, my theta becomes 1. Okay, and this condition also satisfied that at y bar tends to at y bar I mean equal to 0, theta is equal to 0. Okay, but let us take any other combination. If I take this one, t minus t infinity and ts minus t infinity, that means at y bar equal to 0, my theta will be 1, and at y bar tends to infinity, my theta will be 0. So this is also a very good choice of theta, because both of them are making my life simple. Okay, but I will choose this one. And why this one? Because my Ts is greater than T infinity, that is why. That is why this Ts minus T infinity will always be positive. Okay, obviously this quantity will always be positive again, because my T will be always I mean my T will be always lesser than Ts, so this term will be negative and this term will again be negative, so this term will be positive, but still I will choose this one. Okay, so you should have this concept very clear, that that how should I choose this Tc, Uc, Vc. Okay, so here I will choose my theta as T minus T infinity by Ts minus T infinity. Fine. Now what else I have to choose? Okay, x and y, obviously x bar is equal to the characteristic length, or if I am given the length of the plate, then that will be the characteristic length. Y bar will be y by delta. Now this is again unknown, so I can also write that this is yc, okay, and this is equal to y by delta, and this delta is again the thickness of this heated layer. Okay, any other thing that I am missing? U V T X Y, U V theta x bar y. Okay, fine. Now I have to find UC, VC, alpha, sorry alpha no, delta. Okay, so now we will be using our order of magnitude analysis. So I have told you that inertia, viscous and buoyancy all are here not having any kind of competition, they are friends. Okay, so first let us go for the balance of inertia and viscous. Okay, or sorry, let us go for the balance of inertia and buoyancy. Why? Because buoyancy has to be important. Obviously inertia and viscous both has to be important right now, but still to get the value of u, to get the order of magnitude of u, we will balance I and B. So how can we get u? Let us see. So inertia is rho infinity, clear, rho infinity and u c square by L. I have already shown you this earlier, and this will be G beta infinity. Okay, so characteristic temperature, that is delta T, I will write into rho infinity. That means my UC will be of the order of G beta infinity delta T into L. So this is important. Okay, This is important. Clear? Now we got this UC. So how can we get the delta now? So then we will go to the energy equation, and also let us see that what can we get from this balance of viscous and buoyancy. So viscous force is mu infinity u c by delta square, right? This is the viscous force order of magnitude, and this will be of the same order of g beta delta t rho infinity. That means my uc by delta square is of the order of g beta delta t rho by nu, that will be mu by rho. So nu infinity, okay. So that means my delta square is of the order of g beta delta t by nu infinity whole to the power minus 1 into uc, okay. Now if I put this one, that is delta square is of the order of g beta delta t by nu infinity whole to the power minus 1 into g beta delta t L whole to the power half, okay. So what I have done is I have put this value of UC, this order of magnitude of UC here. So this will be equal to what? G beta infinity delta t, okay. So okay, I will take this term, so this will be minus half L to the power half and nu infinity whole to the power minus 1, okay. So now let us see that how can I incorporate all these terms. So I have to find this delta by L. So I will divide by L square in both of the sides, okay. So g beta delta t, now I can write here this square nu infinity square whole to the power minus half, so L to the power half, okay, by L square, right. So that means this will be into L to the power minus 2. Now half minus 2 will be what? So this will be minus 3 by 2, right. So minus 3 by 2. So if I have to incorporate it here in the bracket, so then g beta infinity L cube nu infinity square minus half. This is our well known Grashof number, okay, gr based on L whole to the power minus half, okay. That means our delta by L is of the order of Grashof number whole to the power minus 1 by 4. So if you compare this with the boundary layer theory, then you will know that in the boundary layer theory, we obtained delta by L of the order of RE L to the power minus half, and here this is Grashof number. So Grashof number is actually your measure of the buoyancy force by viscous force, okay. So actually in the natural convention, buoyancy takes the role of the inertia if we think of the forced convection. So in the forced convection, inertia drives the flow and viscosity opposes the flow. In the natural convection, buoyancy drives the flow and viscosity opposes the flow. So comparing these two, we can say that Grashof number whole to the power minus half is actually playing the role of the RE, the Reynolds number, okay. So this kind of analogy is very important, and also the basic significance of Grashof number, the buoyancy force by viscous force. So if you go to any kind of small interviews like PSU, like any kind of company, then you will see those kind of things. So here if I have to say that my delta by L is much less than 1, so this will be true only if my Grashof number is large. Okay, I mean in the boundary layer theory, the REL should be large for the delta by L to be much lesser than 1, and here the Grashof number is playing actually that role. Okay, so here this is our UC, this is our UC. Okay, and our VC should be delta by L into UC. This should be our VC. Okay, so that I mean everything becomes of the order of 1. Okay, everything becomes of the same order. So see, use U by UC, and V bar is what? V by VC, and V by VC is this one. Okay, so now delta by actually V is much I mean less than 1. This V is much I mean lesser than this one, this UC, but this V by UC, although it is much lesser than 1, this delta by L, this is very small, and that is why this 1 by delta by L will shoot up to make all over the term of the order of same as U bar. Okay, so this should be your VC. Okay, so I have already told you the theta, x and y. So I have already found the order of magnitudes of this delta, UC and VC. So in the next lecture I will be doing the non-dimensionalization of the equations, and then we will see that how to solve them. Okay, so I will ask you to try out by yourself the non-dimensionalization of the equations. Okay, until that, goodbye, take care and thank you.